Welcome back to Fujitsu Forum TV, where we continue to bring you live and exclusive coverage from events at Fujitsu Forum 2019. Up next, it's our final keynote of 2019. From mathematical to industrial optimization, taking you through this is Dr. Joseph Reger, CTO and Fujitsu Fellow. Ladies and gentlemen, enjoy.
Is Dr. Joseph Reger. Now, since the beginning of humanity, mankind's main aim has always been to optimize our lives. Today, we're at the beginning of a new era where possibilities are limitless. And Dr. Reger is going to talk a little more about how that has come about and how the world is benefiting from this transformation. So, without further ado, let's please welcome to the stage the Vice President of Fujitsu Fellow and the Chief Technology Officer of Europe at Fujitsu, Dr. Joseph Reger.
Thank you, Louise. Thank you. Good afternoon, everyone, and welcome to the technology session of Fujitsu Forum Europe 2019 in Munich, Germany. And this year's topic is optimization. Can I ask you a question? When was the last time you optimized something? In all likelihood, it was just a few minutes ago when you walked down the aisle in the auditorium looking for a seat. You chose the best seat available. That's exactly what optimization means, and I have a definition of the Cambridge Dictionary here that describes it in very simple terms and very precisely. Optimization is the act of making something as good as possible. Not absolutely the best, not whatever it takes, as good as possible according to circumstances, time, and given means. Optimization is finding something as good as possible. We will come back to that. Now, we human beings do that all the time. We've been doing that from the very beginning. It's our second nature. We optimize without even thinking about it much. We started to optimize on a small scale in the caves, and we started to optimize on a large scale when we built agriculture. Very soon, we started to optimize how and where we build our fortresses as the infrastructure of that time. In modern times, we optimize where and how our modern-day infrastructure is built, like traffic. We optimize our networks. That's before. We optimize the networks even if there are a number of virtual networks running on a simple physical network, and the complexity is higher. We developed very complex financial markets, and we optimize for that. We optimize our instruments, we optimize our portfolio. We optimize all aspects of manufacturing. Here, how robots build a car. We optimize our warehouses, how we store goods in them, in what sequence do we take them in and out. A very similar problem is sequencing again at sea. In the seaport, you want to optimize the sequence you take in the cargo ships to unload them, because that can make a huge difference in the logistics. And I could go on. There are millions of examples how modern life and the whole industry can be optimized. So if that's the case, where's the problem then? Just please go ahead and optimize, and we are all fine. Well, there is an issue, though, coming at us. We are hitting limits of what we can do. It turns out that the mathematical nature of these problems is such that they become exponentially bad if the number of components, the number of ships, the number of goods in the warehouse, the complexity of the network, the data packets traveling, the robots working on a car, if these number of components are increasing, these problems become exponentially difficult and we are hitting the limits of what we can do. But there's no choice. We need to carry on. Optimization is the way to survive on the planet Earth, where even nature optimizes according to the laws of physics. For example, how water flows. And plants optimize themselves for demanding environments. Now, the method they use is called evolution, and it's a very accurate method. It just takes a little bit of time, but that's beside the point. Plants optimize. Animals optimize, not just themselves, but their whole environment, often contradicting the optimization done by nature. What you see here is a beaver dam. And here's the engineer who has built it. He obviously disagrees with nature's ways of optimizing water levels and water flows. The beaver is an excellent engineer. But here comes the physicist of animal kingdom, the archerfish. Look what it can do. This is an experimental setup. What you see is a water tank. The fish is underwater, and at the top, marked by the red arrow, we have a bait, a large insect or something like this. The fish is underwater, and this is what it can do. It hits the target with a water jet that breaks in flight, and it has an angle in it. Now, that is at least 3 disciplines in physics that you need to optimize for. First of all, there is optics. We know that the surface of water breaks the light. The target is not where it seems to be. So the fish needs to shoot low and optimize for optics. But the water jet has a weight and is pulled down by gravity, and therefore the fish needs to optimize for that, and it needs to shoot high. And then the third physics discipline that's needed here is that of hydrodynamics. This is a pulsed jet that undergoes a hydrodynamic instability and accelerates in flight like a jet plane and hits the target with a force that the little fish could never exert using its own muscles. Now that's real physics and a real optimization in physics. Amazing. 3 disciplines of physics. This scenario has been studied by Professor Alberto Vailati in the physics department of the University of Milan in Italy. Thank you for the video. And it's an amazing example of optimization, and I'm showing it just to set the bar. I'm showing it as a way to sort of have a high bar that mankind should reach and maybe surpass and outperform it. And we can. We can because there is something unique to us that's not available in animal kingdom, and that's the use of science, and that's the use of mathematics. Now, in simple math terms, the job to find an optimum is to find a combination of variables. These are the parameters in the system that can change, variables. So find a combination of variables so that a function, typically a cost function, is minimum. What you see here is a single variable function. The values of the single variable are put on the horizontal axis, and the values of the cost function for each of these values is shown on the vertical axis. A very simple function. It's actually a parabola, and it's very obvious where its minimum is, very visible clearly by the naked eye, very easy to find. But of course, in mathematics, we need a method to determine it for all kinds of other functions as well, and to do it exactly. The best thing, if we are looking for minima and optimization, is an exact method of math. We derive the result and determine the minimum and be done with it. And here are the steps what to do in this case of the parabola. Now don't get hung up on it. What I'm doing here is I'm taking the derivative function, which is a description of the slope of the function at any one point in time. If the slope is pointing downwards, then we know we are not in the minimum yet. And if the slope becomes 0, then we are at the bottom because there's no slope anymore. So that's what I'm determining here, and it's obvious the minimum is at minus 5.8. Don't get hung up on it. We need to learn this in school because math is important for everything that I'm going to use later. But in real industrial optimization problems, these exact methods fail. The functions that we are using are simply overly complex for that. Now, if we can't be exact, or we can be approximate. And there's a whole area called numerical optimization with the use of computers. And what we do there in the simplest cases is try to determine the slope approximately. Take 2 points on the curve close to each other, determine the difference in height, and that's an indication of the slope. And if that slope is pointing downwards, slide on the curve like rolling a ball on the curve. Slide on the curve until that slope becomes 0, at which point you hit the bottom. This is not exact, but very easy to do with the use of computers. And there's a whole family of methods. You might have heard the terms gradient method or steepest descent. They're all related to that. And they get only in trouble only if the function has several minima. Here you see 2. On the right-hand side, there is one that's called a local minimum, because there's another one that's even deeper, and that's a global minimum. Obviously, that will be the more desirable one. Now, if we start our approximate method by just rolling balls, we might end up in the wrong one. And for that, we could just simply do it a couple of times, start here, start there, collect some statistics about it, and then determine which one is the better of the two. But industrial optimization problems don't have 2 minima. They have very many of those, very many local minima. And because of that, these methods are not really efficient for them. Now, do we have to be efficient at all? I mean, we could just use brute force and simply go through all possibilities, evaluate the value, compare it, find the minimum, and be done with it. We could do that. In this case, take 10,000 steps, scan the horizontal axis, compare the values, we are done. Yeah, we are if there's only one variable. But these functions don't have a single variable, even if they just had 2, at which point the curve becomes a surface, then it's not 10,000 anymore, it's 10,000 times 10,000, which is 100 million. And if they have 6, 7 variables, which is a ridiculously small number in industrial optimization, we would need the fastest supercomputer for more than a year to do it. So, interesting situation. Exact doesn't work. The functions are too complex. The approximation methods do not work because there are too many minima. And this kind of brute force methods don't work because there are too many variables. These 3 are interrelated, of course. So if we can't do all this and can't use brute force, then we could try to think about something that I would like to call smart force. Let's do a kind of probabilistic random sampling. And this is a very interesting little exercise, very enlightening. It takes a minute, but stay with me because we are going to amuse ourselves. Now, you remember the value of pi in mathematics? We need that if we want to compute the circumference or the area of a circle. The circle has a radius of r, so the area of the circle is then pi times r squared. That's what we all learn in school. Pi is actually an irrational number. It has infinitely many digits. And here I just have a first few of them. And everybody might remember maybe 8 of them or so, depending on your ambition. But what happened if you didn't remember the first 8 digits of pi and needed it? What could you do? Well, here's something you could do. Look at this square. it's 1 meter on the side, and obviously I can fit into that square exactly a quarter of a circle. The radius of the circle would be also 1 exactly. Now, the area of the circle is simple, 1 times 1, 1 square meters. And the area of the, the area of the square is 1, and the area of the circle is a quarter of pi, because r is 1, r square is 1, and therefore I'm dealing with 1/4 of pi. That's the area of the circle inside of the square. Now, if I just started to throw stones at random into this square, randomly, then obviously all of them fall into the square, but not all of them fall into the circle. So I would just simply count the number of stones that end up in the circle, and the probability of that will be proportional to the area of that circle. So with that, throwing stones into the square and counting how many of them end up in the circle, I will have an estimate of 1/4 of pi, so I just need to multiply by 4. So we do this with a computer. And if you just do 100 attempts, the error you make is less than 1%. Actually, it's 5%. So if you do it 1,000 times, it's 1%. And if you do it 100,000 times, it's 1/10%. It does oscillate a little bit, but it settles in. So it seems that this random sampling method can be used to estimate values with a quite high of an accuracy. Now, I'm not suggesting you should do this every time you need the value of pi. I just introduced a method called Monte Carlo simulations. And Monte Carlo in the name refers to the city with the casinos where random processes are generated by rolling dice, the gambling. So this method is called Monte Carlo simulations. Very important in optimization of industrial problems. If you really need the value of pi, you just find the key on your pocket calculator that says pi on it. And if you are a finance person, you will not have it. Financial calculators don't have it. Then just please remember this. 22 divided by 7 is a very close approximation of pi. It's much easier and much more accurate than the Monte Carlo that we did, but that's totally beside the point, you understand. Now, the point is that probabilistic methods play an important role in industrial optimization. But since the cost functions are so complex, we can't just randomly, with equal distribution, throw in those stones and see what happens. And that would be a very bad sampling, very low quality, very inefficient. So we need something better, and that better method comes through physics. The inspiration comes from physics. What we do is we use a method called annealing. In annealing, we don't start with the complex function on your right-hand side immediately. We start with something much simpler, where it is easy to find where the minima are, and the system is driven into those minima in the course of simulations. And then, step by step, slowly and gently, we turn on the complexity of the function in small increments, very slowly. Every time we find the minima and stay with the system in those minima and turn on more complexity, find the minima, keeping the system in low-lying states all the time. And when we end up at the end with the full complexity of the function, the system is still in very low-lying minima. Now, these might not be the absolute minima, but they're very close to that. So again, as we said, for optimization purposes, just enough, because we are looking, given the time and means, for the best solution as good as possible only. Now, in real life and in practice, we find that it's easier not to evolve the function like I just described, but do something equivalent to it, and namely enable the system to not see the complexity in the beginning. We give the ability, grant the ability to the system to jump over barriers between minima, and thereby not seeing them really, and therefore not seeing the complexity of the whole system. So big jumps are possible in the beginning, and slowly, gently, we reduce the size of the jumps and therefore trap the system in some states. But there are low-lying minima at the end of the simulation. And with that, we do something that we could call simulated annealing. That's an equivalent approach. Now, a particularly efficient way of overcoming barriers is not to jump over them. Instead, cut through, tunnel through them. And that's where quantum computing and quantum physics comes in. We can use the phenomenon from quantum physics called quantum tunneling, which is the ability of the system to cut through, tunnel through energy barriers. This seems to work very well, which is why quantum annealing is such an efficient method. It seems to be working very well because, as it just happens, many functions, cost functions of industrial optimization are such that the barriers are quite high, but not that wide. And quantum annealing is a very efficient method to work with those slim barriers. Now, I know, quantum annealing is not the full quantum computing. There is more to quantum computing than just quantum annealing. And we will need full quantum computing someday. A general, universal quantum computing will be needed at some point in time. But industrial optimization problems are very well suited for quantum annealing, and therefore we shouldn't hesitate and use this technology now because it's available. Now, having said all that, Fujitsu's annealer is not even a quantum annealer, and therefore it's not a quantum computer. It's a very special hardware architecture that is being built by using available semiconductor technologies, and therefore we call it a digital annealer instead. It's a special architecture that does things like quantum tunneling. It works like superposition, and it works like entanglement of quantum mechanics. It works like, and it works very well. It is very close to what quantum annealing can do, both in the quality of minima we find and in the speed with which we can work. Very, very efficient, and the software is almost identical. Actually, it's for practical purposes identical to what we use in quantum annealing. And this technology is without the burdens and the issues of quantum computers. Therefore, we can call it a bridge to the quantum world, a bridge technology, and this is therefore quantum-inspired computing. Now, ladies and gentlemen, optimization, and in particular industrial optimization, is a very democratic race. Anyone can participate, no matter what method, based on what theory, using what equipment. Whether it's quantum or not, doesn't matter. If you find the better minimum in about the same time, or if you find similar minima just much faster than other methods, you win. And the digital annealer makes this race even more democratic because it's an available technology, available now, very affordable too, and it doesn't need special operating conditions. Anyone can start immediately and apply it to real industrial problems now. And some companies have already started. So let's see what they are doing with these possibilities. You see, one of the most complex things mankind have ever created is our communication networks. Obviously, there must be some complexity challenges there. And we have my first guest for that topic. Please welcome a technology expert and innovation architect at Deutsche Telekom, Mark Geitz. Mark.
Okay, thank you.
Hello, Mark.
Hi, Joseph. Thanks for inviting me on stage.
Please settle in. Mark, let's start with a very quick overview of Deutsche Telekom and what the company is doing.
Of course. I think most people in the room might know Deutsche Telekom as a company. Just brief, so Deutsche Telekom is one of the world's leading network operators. We are actually giving services and products in the telecommunication area to our customers, 200 million of them in about 50 countries worldwide. Besides high quality telecommunication products, I mean, it's not so well known that we also have set up high standards in terms of data privacy, also climate protection and diversity.
And in what part of the whole telecom group do you work?
Yeah, so I'm personally working for the Telecom Innovation Laboratories. T-Labs, it's located in Berlin, and we are the R&D unit of our company. So our mission is to scout for solutions and technologies ahead of time. So we're talking about time periods of 3 to 5 years. And it took about 1 year ago, we started with quantum technology as part of our AI portfolio. And I mean, we scouted use cases, we set up technology partnerships, mostly with hardware vendors. Yeah, we looked for expertise in our own company, and we coordinated everything with our academic and technology partner network.
So you came from the quantum computing angle, but you use our digital annealer as well, and you understand that's not a quantum computer.
Yeah.
So what do you use it for?
So actually, first, the quantum, I mean, most of the companies that are around, I mean, they see the benefits. The quantum computing is actually promising to us. So excel of computational power for certain specific areas. And we want to be part of it, want to experience it. We want to see how far it takes us, and also what obstacles we will see. Yeah?
I see. And coming back to the digital annealer, so did you start a concrete project with quantum?
Yes, actually we finished our first project already.
Your first project.
Our first use case, which is in the area of Industry 4.0. Yeah, we added it to our service portfolio. I mean, in that we put an annealing technology into a problem that has to do with quality assurance. Yeah, and on the very bottom of it, I mean, there's a very, very hard computational problem. Yeah, where this technology can really solve. And we did it, and we just currently set it up in an industrial production line with a target customer.
And coming back to the annealer, the digital annealer, what did you do with that? What did you look at?
Okay, I mean, we started about 4 weeks ago, just at the beginning, a project with the experts here from Fujitsu in Munich. And we tried to apply the digital annealer to let's say, one of the hardest projects or problems that we have in telecommunications industry, which is the configuration of our networks. Yeah? I mean, the networks are all over. We have wired networks, fiber networks, wireless networks of several generations. Yeah, they're used for access, they're used for transport. All these networks, they have something in common, one optimization target. We want to optimize them in a way to offer the best user experience for our customers, concerning throughput and network latency. If you now look into planning, it's you see there on the slide. I mean, there are tremendous investments that the telecommunication operator is doing from year to year, billions of euros. And now the question is, I mean, it goes for once into technology that is already existing. You also ramp up new cells, or you dig in more fiber. But we're also investing quite a lot of money into the rollout of new technology, like the 5G network rollout. And here, the optimization target is different. We're looking, let's say, for minimizing the investments, but to keep the high service quality that we have.
I see. So there is the question of how to do investment right, how to do the planning initially, the architecture, the layout and everything, and then there is this runtime thing, how to optimize the throughput of the network in is it real time?
It's actually, I mean, from what we see, it's near to real time. Yeah, that's
near
really
to
possible.
real time. Okay. So, Mark, what have you learned so far?
Yeah. So just at the beginning, we just started out a project with the experts, and I mean, we looked at our core transport network. Yeah. So in Germany, yeah, the whole thing. We identified the nodes. Yeah. We identified the links. We know the capacity of the links, and we know the transport that has been delivered. Yeah, from each node to each other node. At the end of the day, we're interested in the best configuration as step number one. Yeah? And I mean, what you do is actually you look at the routes, the different routes that you can take, yeah? And you transfer that routing problem into some kind of energy function. Yeah? I mean, you just mentioned it. Yeah? So it's like a penalty that you do. I mean, take an example. So all the traffic is going via one link. It's a rather bad configuration. It's a valid one, but a bad one. So you have a high penalty. Yeah? So a high energy. Yeah? For a good configuration, so you spread the network across many links, so you give it a low penalty, so low energy. And then you give it to the annealer. Yeah, and the annealer is actually calculating the absolute, or let's say the close to the optimum, so some minimum function that we get back, which we then reverse engineer to the optimum, or to our network configuration that we're looking for.
And while you were doing that, did it disturb you at all that the digital annealer is actually not quantum, but a quantum-inspired technology?
Yeah, in a sense, no. So, I mean, from a user perspective, I mean, you're looking for an answer, yeah, for an optimization answer. And this technology is giving us the answer. From a user perspective, I mean, it's quite beneficial. What you also mentioned, that the models that we do, yeah, I mean, you can apply them to the digital annealer, but also to a quantum annealer when they might become more powerful in the future. Yeah, so the investments are saved. Yeah, but I mean, your chip, the DAU, is powerful already enough to model our network, yeah, which is quite substantial.
I agree. That's quite an achievement. Now, what else are you going to do in the future? What are the future steps?
So we have a couple of optimization problems on the pipeline, yeah, but I think I don't go into them because I think the other speakers will go into the topic. I want to focus to customer relationship management, yeah, and this maybe gives another twist to the technology, yeah. So in customer relationship management, you're looking for good customers, for bad customers, for fraudulent customers. Yeah, you look into what is the best offer for these customers. So it's not optimization, yeah, but it leads to categorization, yeah, and that's some kind of AI technology, yeah, and I'm pretty sure that we can model an algorithm that works on the annealer that can also do this kind of machine learning and artificial intelligence job.
That's very good news because it applies not only to tech industries like yours, but in general, everywhere our customers are present. Thank you very much, Mark. This was very interesting. Looking forward to do more.
Okay.
Thank you very much.
Thank you.
Cheers. Bye.
Bye-bye.
It turns out it doesn't need data packets congesting a network, but it can be physical objects in their network that can congest the network. And if these objects are vehicles, the whole thing is called traffic. And my next guest is the head of traffic management at Hamburg Port Authority. Please greet with me Hermann Grünfeld. Welcome. Listen, Hamburg Port Authority. Hamburg is one of the largest seaports in the world, and it's not even at the sea.
Yeah, that's right. You use 5 hours or 100 kilometers from the North Sea to the port of Hamburg, but I think that's not the really problem.
The problem is probably a different one, namely that your port is huge and there's a bunch of complexities there. Can you elaborate a little bit on the challenges you see?
Yeah, that's right. We have the very great challenge. We have very big vessels. The greatest vessels on the world come to the port of Hamburg. We have cruise ships, we have container ships. One container ship is in the moment maybe 400 meters long or 70 meter bridge. And we have in the moment around about 150 million tons per year. Or you can say that we have 9 million containers we handle each year. And we are in Germany the greatest seaport, and in the European North Range, we are the third greatest port in Europe. And special is that we have a very interesting hinterland. We handle a lot of traffic about the railway tracks and a lot of track of the roads, maybe 50% on tracks and maybe 50% on the road.
So the port authority does not only manage the traffic on water, you manage the traffic on the land as well?
Yes, right. We are the landlord from the Hamburg Port Authority, and we are the owner from the bridges, and the owner from the streets, and the owner from the rail trails. In the moment, we have 140 kilometer streets, around about 300 kilometer tracks, and yes, 800 switches on the tracks, and we must optimizing the traffic between the different traffic.
It sounds like a small city in a bigger city, city in the city, and therefore what every city tries to do, traffic optimization is the job to do.
Yeah,
how are you doing with that?
Oh, heat attack. This is a challenge. This is a very great challenge. I think we have the problem in the future when we have the situation that we very great or a lot of traffic have in the middle of the city. And on the other hand, we have the situation that the city, Hamburg, and the port is own area. And the port area is 10% from the city area. And what is the idea? What is that? What we will optimizing in the first step the traffic on the streets. We will see here on the picture. It's a very simple grid, and in the history we have example a traffic light, and the traffic light work. After the last 100 years, the step by step, green, yellow, and so, and the computer organizes it. But the problem is we have not a really intelligent grid, and the idea is that we make not the junction intelligent. The idea is that we make the grid intelligent.
So individual traffic lights are optimized, but not the whole thing.
Right. That's
I see. And so what kind of results are you getting? What are you looking at currently?
Yeah. We have the proof of concept, and we work with Fujitsu together, and it was very interesting when we see the engineering from Fujitsu, and when we see my engineers in the traffic management, and we work together, and they have the very simple question: what is the good green time for the junction? Was it possible to build the traffic maybe from the east to the west in the port or on another side? And is it possible to make the traffic flow less stress, a little bit more traffic on the road? Is it possible? And we see this is chance with the annealing computing to see this is 10 or 15% better when the traffic flow lost stress on the street.
And is that a realistic scenario, or this is how you started and moving to a more realistic scenario?
We work every day, and it is a very interesting, special thing. In the moment, we have a very short response time. That's okay. And in the next steps, we make a realistic scenario. From the simple grid, we work in the reality area on the port, and we work only with geometric from the junction, and we work with realistic traffic flow, and we measure what is the old system and what is the new system, and I'm very interesting, maybe 10-15% I'm very optimized in the moment.
Very good. What would you say, what could be the next steps if we are all doing this all successfully?
Yes, the next step for successful is a very interesting thing, because I think we work in the moment for 4 or 5 junction. In the next step we make 21. This is a challenge. It's not so easy when this is very great. We have a lot of more optimizing processes in the traffic. And yes, in the future we will combine the traffic with the trains, with the tracks, with the waterways and the ships, with the infrastructure, with the movable bridges also, and the traffic also. And that is very interesting when we work in the future of Hamburg, and I think this is a nice picture you can see.
So do you think there's a chance we could extend this from the port of Hamburg to the whole city of Hamburg?
Yeah, this is a very good question. Thank you for the question. In the moment, we have only 35 traffic lights in the port. That's not really too much. In whole city of Hamburg, we have 1,700. In the whole area in Germany, we have around about 70,000 traffic lights. And in the moment, I think we use it for 500 or 600, maybe 800 traffic lights in the whole area for Hamburg, and have a very good function for the traffic, for the personal traffic, but for the personal traffic in the logistics. That is very important for the city in Hamburg.
You know what, let's finish this first, and then let's tackle the whole city of Hamburg and all traffic lights. How about that? How about that? We can do it. We can do it.
We can do it. We try it,
yes,
and then we hope that this is okay way. Yes.
Thank
okay.
you for
Thank
that.
you. Nice to meet you.
I might have surprised him a little bit. Right. Of course, all those cars in traffic and at the traffic lights need to be manufactured first before they get into traffic. So let's see what we can learn from one of Germany's leading car manufacturers. We have with us today the quantum lead and the technology scout of the BMW Group, Oliver Wick. Oliver. Hello, Oliver. Hi. Please. Listen, Oliver, I looked at your title, Quantum Lead, very nice. So therefore, I'm not going to ask you whether you came through the quantum computing angle to this optimization. So tell us about how and when did you get into it?
Sure. Could I see the next slide? Yes, you have to understand I'm from the research department and not from the production department. That means me from the research department, we have to initialize all these kind of technologies. And the first step was in June 2017, we produced every year a technology radar, and there we identify quantum computing on the list. And we are gone to our colleagues and asked, okay, what is quantum computing? Do you know that? And nobody knows that. And so the actual task for technology scouts are, what is quantum computing? What is the technology there? What kind of different computers there are available? What are the competitors? What are the technologies that, and who are the providers in this way? Yes?
And on this slide, I don't see one provider by the name of Fujitsu.
Yes, sure. As I said, we began with quantum computing technology. And so, as you mentioned very, very well to the audience, that is not really a quantum, it's a quantum-inspired technology.
Indeed.
And we do a lot of proof of concepts, around about 4 or 5 in this way. And so we identify, for the case PVC sealing, I will talk about later. There we used quantum annealers from a Canadian startup, more or less. And so we identify we could not implement the whole problem on this chip. And so we are looking for an alternative technology, and that was the reason why we meet Fujitsu.
Let me repeat that. So the real quantum annealer couldn't do it, but the digital annealer could.
Sure.
Just to the home point. Yeah, thank you for that.
Yeah.
Thank you. Listen, so the PVC you were mentioning, we will come to that, but there are use cases that you study meticulously and systematically, right?
Yes, right. As you see in the background, we have some different use cases. In the enabling part, it's more or less in the research department. There we have machine learning use cases. That means quantum machine learning. Then we have for development, that means car development, some use cases. And one is the optimization case from the right engine. To explain that a little bit, you know all drive now. You have here cars and passenger requests, and you have to match these one. And this is a right engine. And you talk about the annealing case, and mathematically, is that a travel salesman problem? And you can very well use annealing methodologies for that. And sure, then we have the production one, and this is the mentioned PVC sealing, which I will explain later.
So you classified the use cases according to what technology is best suited for, maybe, but some of them are unclassified. They don't have a marker yet.
Sure, yes. I would like to explain the yellow bubble, the very little yellow bubble. You see 3 bubbles. The first one is the quantum annealer, the AQQ. We used that, then we switched to the digital annealer from Fujitsu, and actually we are under investigation or on experiments regarding universal gate-based quantum annealer. You have to understand that we are looking for real business value. We will check all the kind of available technologies. And the first both technologies are more or less for us the low-hanging fruits. Yeah.
So a bunch of optimization jobs here, and I hope we can get a fair chance to compete on everything that says optimization with our gear. But let's just talk about now about the use case and the project, the POC that we did together that we are so proud of, both of us.
Yes, sure. Okay, next slide, you will see a short video about that you can imagine what is the task. Here you can see a car, a chassis, and it is sealed with PVC in order to prevent corrosion. And now you have the task to program the robots that they should do that in a short time with less material and some other key performance parameter. And in the next one, you will see some key performance parameter. In this way, you have different robots. In this case, that was 4. We have a lot of different car models, and you have always to make another path. You have different seams on the car, and you have different PVC nozzles. And if you combine all this complexity together, you will get around about 10 to the 100 possibility setups. And so you have to think about what is the best and efficient optimization for that. And we decided it should be the annealing part, and we checked that with quantum annealing and now with digital annealing together with Fujitsu.
And what did you find?
What we found, this is on the next step, on the next slide. We found actually we could implement our problem to the digital annealer. That means that was for us in progress, because with the quantum annealer we have to make different sub-steps in order to implement that. That means that was the first time that we could run it on an annealer one. And now we would like to make the next steps. The next steps are that we checked if, sorry,
you're going to check what? At some point you will have to validate it for production too, right?
Yes.
Is that at the very end?
That's the variant, all right. Actually, we have it on 4 robots, and now we have to think about the scaling to a whole production line in this way, because then we can use the annealing case in the real manner. And let me add one example where we need real-time requirements. This case is not real-time.
It's not real-time.
It's not real-time, but in the case of the Drive Now, the right engine, We have a real-time requirement. Nobody from us, you will wait to a car. And that will be the next steps where we have to examine all these activities.
I see. So lots more to do.
Yeah.
I hope we can compete. I understand BMW needs to evaluate the technologies.
Yes.
Fine. Business cases have to be built.
We
Fine
are
too.
complete hardware agnostic in this way.
I understand that, but we can still compete.
Sure.
And we will. Thank you very much.
Thank you, Joseph.
Oliver, this was fun. Thank you. Thank you. Now, this was fun and very encouraging and very satisfying too, because obviously we are getting better now than the archerfish. No disrespect. However, I have to say, on a serious note, that we need to optimize more. We are not optimal. Our infrastructure isn't, our resource usage isn't, our networks aren't, our traffic isn't, our products aren't either. We are not optimal. We are not even close to optimal, and therefore we must do more. Natural resources tend to be limited. Artificial resources, not so. Artificial resources like brain power, imagination, creativity, skills, programming skills, math skills are not limited. And computer power is becoming very much less limited as we speak. Our job is to blend natural resources and artificial resources so that we can optimize what's limited by the use of unlimited. Optimize what's limited by using the unlimited. So please, optimize. Optimize the planet, optimize the resource usage on the planet, optimize the life of mankind, every aspect of it. Solve social challenges, optimize the networks, optimize the traffic, optimize the products, optimize the production of your company, optimize the whole company. And while you are doing it, you will be optimizing your own career too. Optimize, everyone. Optimize. Thank you.
Thank you very much to Joseph for such a wonderful insight into optimization. Now, Joseph's speech does round up our keynotes here at the Fujitsu Forum for 2019, but the day is far from over. You can still look in on the breakouts and explore our Digital Transformation Center. So I wish you a wonderful afternoon of networking and discovery. My name's Louise Houghton, and on behalf of the entire team,
Now you can understand why so many people at Fujitsu and our partners are incredibly excited by the power of Digital Annealer. Quantum computing inspired Digital Annealer has the propensity to impact society greatly, as we just heard from Dr. Joseph Reger and a great guest on stage. There is a lot to be excited about, but there's still a lot of work to do. Hopefully that's whetted your appetite around the future of quantum computing and what Digital Annealer is doing right now for Fujitsu. We've got a swift turnaround. It's what, 12:57. We are going to be back to you in just a matter of minutes, where we'll be live looking at manufacturing. Now, there's a sector going through a lot of change at the moment. Similar to the transport interview that we brought you yesterday, we've got the move to the smart factories. We've got the rise of technology, which is complicating the ecosystems. We are going to do our best to simplify the story and help you understand where you should be looking at technology-wise. Stay with us. We have plenty more to come from Fujitsu Forum TV today.